This is Mr. Precella picking up after our break, discussing the compound amount formula. I'd already stated the formula and we've done some examples of it in the first part. And now I want to state something that economists refer to as the effective rate, or you might hear it called the annual percentage yield, not the annual percentage rate. The APR, annual percentage rate, is what financial institutions would call just the stated rate. The APY is the annual percentage yield, and it's referred to as effective rate also. And what that effective rate is, the effective rate, or APY, annual percentage yield, is the annual compounding rate. If you had a bank that was offering money, interest that was compounded monthly, say, and it was 5% compounded monthly, what equivalent annual compounding rate would that be? If you have the APY, then you can compare different interest rates. You can compare monthly compounding versus quarterly and so forth, and I'm about to do an example of that. But first I better state the formula. Lowercase r, and that subscript e just stands for effective rate, is 1 plus I to the m power minus 1. Well, I, we've seen that, lowercase I, we've seen that variable before. It's that interest rate per period. But we don't have m here, we just have n, but not m. So let's make a note that m is the total number of periods per year. So m is the total number of periods per year. And here's a good example illustrating this stuff. Here, I'll put my little formula right there. Bank 1 offered an 11-year certificate of deposit, or CD, at 4.61% compounded quarterly. On the same day on the internet, First Bank offered that 11-year CD at 4.6. Notice it's a little bit lower, isn't it? 4.6 versus 4.61, but it's compounded monthly. So here you're going to earn interest, they're going to calculate interest 12 times, once a month, whereas over here they only calculate the interest 4 times during the year. Find the APY for each CD. Which bank paid a higher APY? Well, when calculating this APY, the length of it doesn't matter. All you need is that interest rate per period and the number of periods per year. This 11 years really doesn't have anything to do with the APY. You see, I'm using my little invisible orange. So I'm sort of marking that out because the 11 year doesn't matter. It's only the interest rate and the number of compounding periods that are significant. So if I put this here, let's break it up. Bank 1 and First Bank. So on Bank 1, let's see, it's 4.61% quarterly. While on First Bank, it's 4.6% compounded monthly. So I'm going to use 1 plus I to the n minus 1. So let's first of all calculate I. I is that stated rate over basically m, the number of compounding periods a year. 4.61 compounded quarterly. There's 4 quarters in a year. So looking at this, I is the stated rate over the number of periods per year. Do you remember us doing that in the last one? Now what's m? Well, m is 4. How many compounding periods are there in a year? M is 4. Over here on the blue side, I would be 0.046 over 12 monthly, 12 months in a year. M is 12. This bottom number here is what this formula is referring to as M. So we go 1 plus I to the m power, then a minus 1. We'll have to punch that into our calculator. And over here, what would it be? That same formula. 1 plus I to the m power minus 1. So we're going to punch these two into the calculator. And where is my calculator? It's right here. I wonder if I can put it to get a decent picture. So there's not too much glare. That's pretty good, but you can't see. I'm just going to have to use it right here. So I'm punching in parentheses 1 plus 0.0461 divided by 4. Close the parentheses, raised to the 4th, and then minus 1. So 4.61% compounded quarterly is 0.04690309 ... And we're told to round this to, we're writing it as a percent, and it says round it to 3 decimal places. So this would be a 4.690%. Now let's flip over and do the next one. Parentheses 1 plus 0.046 divided by 12, close parentheses, raised to the 12th, minus 1.046982333 divided as a percent, so move the decimal point, and then round it to 3 decimal places, 4.698. Remove the calculator. So Bank 1's APY is 4.690. First Bank's APY is 4.698. So this is the higher rate. Okay? This is the better interest rate. 4.6 compounded monthly is better than 4.61 compounded quarterly. So let's see. Let's see if we can answer the questions now. Let's says, okay, the APY at Bank 1, you type 4.690. The APY for First Bank, 4.698. Which bank paid a higher APY? First Bank. So that effective rate, or APY, is a nice way of comparing these interest rates. Okay? Well, let's do another problem. Oh, number 13 is a really good one. Let's do just the one right next. I'll refer to these as based on the problem number where I printed them out, but the important thing of the problem is not really which number it is. So right here, move it up. Okay. A company will need $25,000 in 6 years for a new addition. To meet this goal, the company deposits money in an account today that pays 11% annual interest compounded quarterly. Find the amount that should be invested to total $25,000 in 6 years. Okay. Now, this is not an APY problem. This is just a compound amount problem. So, this one's sort of different from the others. If I drew a time from the ones we did the other day on the first video. The first video in part 1 of this lesson, we were calculating that compound amount, the future value. But on this one, we know the future value. It's going to need, the company needs $25,000 in 6 years. To meet this goal, the company deposits money in an account today that pays 11% compounded quarterly. Find the amount that should be invested to total $25,000 in 6 years. See, this one, we know A, we've got to find P. But we still need to know lowercase I and lowercase n. So let me go ahead and write this. To get lowercase I, we normally divide. 11% is 0.11. Quarterly, that would be 4 times a year. So let's see, if when I punch in 0.11 divided by 4, is that a terminating decimal? If it is, on your calculator, 0.0275, then I'll use that. If it were to just keep going and going, don't round it. Just stick with a 0.11 over 4. So 0.0275. Now n, to get I we normally divide, to get n we normally multiply. So we're going to multiply 6 years quarterly. Altogether there are 24 of those quarters over the 6 years. So now I'm going to plug into this formula. This time I'm plugging in for A, and P is what I don't know. P times 1 plus I. I'm going to go ahead and do that 1 plus I right now. 1 plus 0.0275, 1.0275 raised to the 24th power. To solve this for P, I'll divide. And you know what? I don't really need those parentheses there. 1.0275 to the 24th power. Oh, let me go ahead and move this up. And, I guess it's time to bring in my calculator. I'm going to punch in 25,000 divided by 1.0275 raised to the, ooh, wait, let me clear, 25,000 divided by 1.0275 raised to the 24th power, and that's going to give me a $13,036, and if we're rounding to the nearest cent, 95 cents. Now, let's see, how does it tell us to round? Oh, they say round to the nearest dollar. So I should actually be rounding this to 13,030. Do I leave it as 36 or make it 37? $37. So lights have gone off for a moment in this room. This motion light sensors are really fast. So this one's different from those other ones in that we were calculating the present value. So if you have to find the present value, you're going to wind up having to divide. Okay? Now, let's do another one. Oh, number 14. It's really short one. Let me get a sheet of paper. This one deals with inflation. And one word that's conspicuously absent in number 14 is the word compounding. But whenever we're talking about an inflation rate, that's always an annual compounding rate. Inflation has been running at 3.05% per year. And a new car costs $25,300 today. What would it have cost 4 years ago? Oh, wow. This one's sort of tricky because it says today, but let's look at this. If inflation has been running at 3.05% per year, that means compounded annually. And a new car costs $25,300 today. Might be tempting to put the $25,300 right here, but then it asks, what would it have cost 4 years ago? So this $25,300 is actually the future value, and we're going back to find a present value. What should our answer be more or less than 25,300? It should be less, okay? And this is 4 years. So actually, this one's very much like the one we just finished doing, number 13. A equals P times 1 plus I to the N. Here, A, we know that, 25,300. We've got to calculate I and N. I, that's the stated rate, 0.0305, over what? How many annual periods are there in a year? Well, just one. 0.0305 is I. And N, well, how many annual periods are there in 4 years? 4. So plugging in 25,300 equals P times 1 plus I to the nth power. Divide both sides. It's very much like the one we just finished doing. Divide. Bring in my calculator now. Let's see if I clear that. Okay, so 25,300, oops, 25,300 divided by 1.0305 raised to the fourth power, $22,435, and I believe it said round to the nearest cent. What would that be, 13 cents? Okay. So just remember, inflation is always an annual compounding rate, and it might not say it. It just says it's been 3.05 per year. It didn't say compounded annually, so you sort of assume that. Number 15 is just like another one. Let me see. Let me go back. Number 11. Two partners agree to invest equal amounts in their business. I know I start going fast through these, so if you need to pause the video, if you're working them out with me, if you need to pause it and work through it and then see if you're doing the same thing I'm doing, that would be a good thing for you to do right now. Okay, when I start working it out, pause it and you see if you can work it out too. Two partners agree to invest equal amounts in their business. One will contribute $10,000 immediately. The other plans to contribute an equivalent amount in 6 years. How much should she contribute at that time to match her partner's investment now, assuming an interest rate of 9% compounded quarterly? Okay. So could you draw a timeline? We're given that $10,000. Where would it go on this timeline? Here or here? One will just contribute $10,000 immediately. Then there's a 6 year, 9% quarterly. I like drawing these many timelines. I always see a lot of people doing these and they don't have that drawn. For some reason I'm visual like this. I love to see that timeline, especially as the problems get more involved, as they will in the next few assignments. Or next two, you might really want to, actually next 3 assignments, you might want to really practice drawing those timelines. Well, one's going to contribute $10,000. Are you thinking that the $10,000 would go right there? The other's going to contribute in 6 years. The future value here is what we're going to try to find. Okay, so we use A equals P times 1 plus I to the N. Let's go ahead and write it out. I is 9% quarterly, so that's 0.09 over 4. 0.09 divided by 4, does that terminate? Yes, 0.0225. In we normally multiply. 6 years quarterly. Altogether there'll be 24 quarters. So now I'm going to plug in. P we know. P is the 10,000. So I'm writing A equals P times, I'm going to do the 1 plus I in my head. 1 plus 0.0225 is 1.0225 to the N power. So punching that in. This trusty calculator, which you can't see very good. Maybe it's a little less glare right there. So here I'm going. 10,000 times 1.0225 raised to the 24th power $17,057. And how are we told to round this? So 2 decimal places, so dollars and cents. 0.6. So can y'all see that? Is it 67 cents? Any questions there? Well, I think that's probably enough for this lesson over compound interest. It's important that you work on it and stay caught up with me, okay? We're going to start discussing annuities the next time. And with annuities, that's going to involve a series of equal periodic payments. That would be like paying off a car loan or paying a house loan or saving for retirement. Okay? That's different from just this compound amount formula where you're depositing one lump sum and then paying back or receiving one lump sum. There's not a series of equal periodic payments. The next one, we'll discuss those, okay? So this was the compound amount formula, and the formulas you need to know for this are effective rate and the compound amount. Right there. Okay? So make sure you get familiar with these, and probably your teacher lets you use an index card on the test. So this is something that when you have it on a test, you might want to write it on the index card, okay? Because we're going to get several formulas over these as we're going through all of this, okay? So I will talk to you later when we're discussing annuities. Bye-bye.